Welcome to this Meow seminar with Mika Göös from EPFL. Mika has done truly foundational work in communication complexity, has also leveraged this to prove beautiful results in many other areas, one of them proof complexity. And today he's going to talk to us about TFNP and among other things, hopefully explain to us what that means. Mika, please take it away.
Okay, thank you. Yeah, so I kind of switched up my plans a little bit compared to the abstract that I submitted. So this is a project that we've been working on with, loads of people. So my students, Robert's students, and Alexandros Hollender, who I guess is not here, is a postdoc at Oxford. And so this has nothing to do with communication complexity. I'm really happy I'm kind of breaking out of my old molds here. The project is all about trying to understand the complexity of search problems. So I guess classically in complexity theory, we often say, okay, it suffices to study decision problems. That already allows us to formulate P versus NP, and that seems like enough. But there is actually a separate theory for what are called total NP search problems. And so this project is all about just trying to push that sort of theory forward. So so we have a bunch of results, almost too much. I can only concentrate on few this week. I decided in the end to talk about the simplest results that we have, like simplest to present, so they don't require any background. So those are new collapses of some of these search problem classes. We really started this project by trying to prove separations. So those have tight connections to this area of proof complexity, which I think most of the audience is kind of experts on. But that's all very technical. I want to keep it very simple today. It's Monday. We're all tired from the weekend, I'm sure. And so I want this to be like a very chill sesh. I want you to understand the proofs completely. So maybe I'll just start with defining TFNP. So the idea is that we study search problems. So TFNP, so it means total functional NP. So what is a TFNP problem? So it's been given by some polytime computable relation. So some algorithm gets as input strings x and y, and we require this to be polytime computable. So think of very much like a polytime machine that checks an NP witness. So X is my input to the problem, and NP would be characterized by, you should output yes for X if there exists some Y that causes this verifier to accept. Except when we turn this into a search problem, we're just not asking like, does there exist a Y for every X, but rather find a Y. So the input is just this string X, and what you should output is any Y, and let me just restrict the length of Y so that it's a polynomial in the length of X. So restrict that such that the verifier accepts. Okay, so this is like a certificate finding problem, and also known as FNP problem. So F functional, maybe better term would be relational problem. What makes it a TFNP problem is we additionally assume, well, maybe I shouldn't put it in parentheses, that this relation is total. So that means that for every X, there exists at least one Y that causes the verifier to accept. So as a decision problem, it's kind of trivial. If the NP decision problem always has an answer yes. So for every input, yes, there exists a y. But this is all about trying to find one of those certificates that cause the verifier to accept. So TFNP is then the class of all such total search problems you can define. And maybe the best way to kind of get into it is I'm just going to give you an example of a problem in TFNP. So my first example is called iteration problem. So what it's interesting of these problems is that they are somehow guaranteed to be total. That's it's interesting that you can kind of syntactically define relations that are guaranteed to have needles in a haystack, so guaranteed to have these y's, yet oftentimes we believe they're hard to find. So here's a prototypical example of such a problem. So here the input to iteration. Well, I'd like to think of it as that you're kind of given an implicitly defined DAG, a directed acyclic graph, and I'm going to ask you to find a sink in the DAG. It's just, I have to be a bit more precise. How is this graph given? It can't be a polynomial sized graph that you can kind of explore in polytime. It has to be somehow an exponential sized graph that is defined implicitly. So as input, you're actually just going to be given circuits. So two circuits, S and V. So they map n-bit input strings to, let's say, n-bit outputs. And I interpret such circuits, which by the way are polynomial sized, so polynomial in n. And so they implicitly define a DAG. So this defines a directed acyclic graph G with capital N nodes. So capital N is 2 to the n. So every n-bit string is a name of a node in my graph. And it's a directed graph defined so that I have a edge from, well, directed edge from, let's say, V to U. So that's an edge in my graph if the following conditions are met. So firstly, the circuit S for successor. So if I compute the successor of V, the output of the circuit is U. So that's one condition, but I also want it to be the case that when I evaluate the second circuit, which intuitively now gives a value or a numerical potential value to each node. So I just interpret the n-bit output as a number, and as numbers, I require it to be the case that when I go from V to U, it needs to be the case that the potential value is increasing. So if I evaluate the values of both nodes, then as I take a step from V to U, following this successor, then the potential value needs to increase. So let me just draw a picture of what this looks like. So you have a bunch of nodes. So each is represented by an n-bit string. And so let's see. So each guy is going to point forward according to what the successor circuit outputs. So maybe I look at the first node, it points to somewhere else. And this is a valid edge in the graph if the potential values increase. So in my pictures, I think of the potential values as increasing when you go down this picture. So every edge I'm going to draw in here is going to have an increasing value. And so it can be that many different nodes point to the same successor node. So I'm going to get this graph which has maybe unbounded in degree, but out degree is always at most 1, because that's how you're going to point forward. I guess I also allow you to point to nothing. So like if your successor is maybe outputting the name of the node itself, like some kind of attempting to do a self loop, well, that's forbidden because the potential value should increase. So some of these nodes might be just isolated. So that's the input and how I interpret it. Output, given this exponential size graph, you're supposed to find a sink. So output is what I call a proper sink. So that's a configuration between two nodes. So one of lower potential pointing to one of higher potential, such that the high potential guy does not have a successor. So I just indicated with a bottom symbol. So it's like, at least in my picture, what are the sinks in my picture? There's only one, basically this guy here. And the way I would like formally solve it is I would name the node above the sink, the one above the sink, and it's easy now to certify that, okay, this guy above the sink is pointing forward truly, but then the path stops there. So that's a proper sink. So in particular, these isolated nodes, they're not considered as solutions, they're not proper. So there's one problem with the definition so far. I wonder if people can see it. Like intuitively, if I have such a DAG, there must be a proper sink, except there's one boundary case I didn't cover. So I want some audience involvement, maybe in the chat. I claim this is actually not yet a total search problem. Why is that?
I mean, it would be nice to know that there is an edge, no?
Yeah, so it still could be possible that the whole graph is empty and that doesn't have a solution. So just as a kind of to exclude this possibility, I'm going to explicitly say that there's at least one node in the graph that does have an outgoing edge, and that's the node named 1. So it's like you're supposed to output a proper sink or determine that this distinguished node is not like a source. So you're also allowed to output the node named 1 if it doesn't have a successor. Okay. So now I've made it into a total problem. So either this distinguished node is isolated or it points forward, in which case I can just continue iteratively applying successor to eventually find myself a proper sink. Okay. Questions about iteration problem? It's really important, actually. I'm not just giving out random problems as examples for fun. So this problem is important because it kind of captures a whole complexity class of problems. So
just a question, do we care about the circuits? I mean, how should we think of them? They're just given, what can we do with them? They're black box, we can evaluate them, or can we like inspect them in any way? Or
Good question. So for the purpose of TFNP theory, the poly-sized circuits, you can do whatever you like with them, but nobody knows how to do anything else with them except to evaluate them. So there are no like techniques that would kind of look inside the circuits and deduce anything useful. Like the best we know of currently is to treat them as black boxes. And so that's why sometimes you can define versions of this theory where you explicitly say that the circuits are black boxes. And so these you can do this formally by studying like relativized versions of these classes, so relative to oracles. And once they're black boxes, you can actually sometimes show unconditionally that these search problems are hard. So those are the two settings. But for this talk, for the results I'm going to prove, we stick with the Turing machine model. where you do have the circuit? Good question. Okay, so let me define a whole class of problems called PLS, for polynomial local search. And it's just every problem that's reducible to this iteration problem. So it's a class of problems P in TFNP such that P reduces to this iteration problem. I should maybe explain what reduce means, because it's not a usual decision problem. To reduce search problems to one another, you have to use a definition that's slightly more complicated than maybe for decision problems. So just quickly to define it, what does it mean for two TFNP problems to reduce to each other? A reduces to B. So this means that there are some polytime functions. So certainly one function, which one has even for decision problems, where it transforms inputs of type A to inputs of type B. So if I have an input x to this problem A, I can apply this function f, and I can get an input f of x to problem B. So now you can imagine that if I have such a transformed input and I have an algorithm to solve B, I would like an algorithm to solve A. So imagine this f of x being fed to an algorithm for B. So maybe I have some black box that solves B. So that kind of an algorithm would output some y such that it's a solution to f of x. So y solves the instance f of x for B. That's what a black box would produce. So we need to to get an algorithm for A, we need to be able to map this solution to B back to a solution to A. And so that's why this definition of reduction uses, I guess, still a separate function g. So that's a function you apply to y so that you get a solution to the original instance. Okay, so it's really, a reduction is given by two polytime computable functions, one transforming instances, the other transforming solutions back. So reductions are really important concept. We're going to play around with them today a lot.
And I guess maybe it doesn't matter, but technically speaking, the G function, do you need it to be defined on all of B or just the image of F?
I would just say B takes an n-bit input, produces something.
Okay.
And the correctness may not talk about all possible y's, but certain structured ones.
Okay, so then in practice, you're saying so basically you're taking this fx thingy and applying g to it, and then you want this condition that you have at the bottom to hold. That's the minimum. Yeah, makes sense.
Sorry, G shouldn't take x as input as well?
So it doesn't hurt if I include it in there. I just wonder, I would believe it makes for the same definition, although I'm not sure if it's clear on the spot. But in some sense, this B guy, it doesn't know what x is. So it was only given f of x. Mm-hmm.
Okay.
Yeah. Okay, so let me, before I kind of tell you what we've done, I'm just going to give you another example of a search problem, and we'll play around with it a little bit just to get used to these ideas. So it's kind of like the second most important problem in TFNP theory. So this is called the end of line problem. So here again we're being given an exponential sized graph as input, implicitly described. So this time I have circuits S and P for successor, and P stands for predecessor. So the graph this defines is one where I have a directed edge from V to U. So that's an edge in my directed graph. If, well, I want so U to be a successor of V, like in the iteration problem. So if I apply the successor function to V, I get U. But I also want there to be backwards pointers, so that if I'm at U, I can step back to V. So the predecessor of U should be V. So these two functions are kind of supposedly inverses of each other, and at least whenever there's the graph has an edge between two nodes, then it means that the two circuits kind of are invertible. So I guess the picture here is that there's no potential right now anymore. So now I just have a bank of nodes. So there's no inherent ordering to them, no sense in which one has a higher potential than another. And what the two circuits describe is, well, each node has at most one successor, but also each node has at most one predecessor. So the kind of a graph that's created is just a, well, it's a union of directed paths. I guess we can allow self loops as well, that's fine. So that's the kind of graph given as input. What should you output? So similarly, we want you to kind of find a sink or an end, well, I guess it's in the name, end of a line. So you're supposed to find a sink. So that's a node that doesn't have a successor or a source node. So some guy who doesn't have a predecessor. But we also kind of need to initialize this problem and promise that the graph is not empty. There's something happening. So there is this border case where I say, or you can output the node called 1 if the one node doesn't have a successor, or if it's not a source. Or I guess, so it has no successor or has a predecessor.
Which takes care of the case when you have a one big cycle, right?
Yeah.
Which is another thing. Because
So
we can have cycles also. I mean, you said lines.
True.
There's nothing forbidding cycles.
So now, so if this promise in parentheses is not violated, it means that the one node has no successor. It just kind of shoots out a path somewhere, and our task is to try to find, well, either the end of that line, so that would be here in red, or what is okay is also to find a source, well, non-distinguished source node, like this. So all the guys I've circled in red are feasible solutions. I guess if I have an isolated node, I can also count it as a solution or not. It's not super important. If I have an isolated node, I think for simplicity, I always implicitly think of them as being self loops. That's kind of a technical detail. Okay, so let me challenge you to kind of identify what this problem is in more traditional proof complexity language. So I claim that this end-of-line problem is basically our usual pigeonhole principle. So I claim that this end of line reduces to Pigeonhole principle, which let me just define it in the language of TFNP. So Pigeonhole principle would be, again, like an exponential sized encoding of the principle where I have a bunch of pigeons. Well, let's say capital N of them, so exponentially many pigeons. And I have some circuits that are able to map those N pigeons to N-1 holes. So on the left side, right side of my graph, I have only N-1 nodes. And if I give you a pigeon or a hole, there's a circuit that tells me what's the pigeon that's supposed to be mapped to the hole. So it's like I have pointers both ways. For each pigeon, I know where it's mapped to. There's a circuit computing this. Each hole is going to point in the other direction, telling me which hole. So each hole is going to tell me which pigeon gets mapped to that hole. So I guess the picture here should be something like this. So every, if I fix the circuit, so it defines some sort of an attempted bijection. So bijectively, but what I count as a solution for Pigeonhole is like some hole or pigeon that is not mapped properly. So in this case, I guess these are the guys that are left empty. Okay, so I claim that this end of line is just the usual Pigeonhole principle. So there are actually reductions both ways. Let me just kind of attempt this direction I've written down here. So suppose I start with a end of line instance. So I guess locally it could look something like this. I have my distinguished source node and then some sort of a path going in here. How would you transform like this piece of an end of line instance into this kind of pigeonhole style with left and a right hand side of nodes? So yeah, I take answers through chat as well if you guys have ideas, or you can just speak up.
You could make each node a pigeon and all except for the first one a hole.
Yeah, I think that sounds right. So I take each of the end of line nodes and I split them into two. So this is like what the reduction is doing locally. I take each except the distinguished node and I split them into two. So the middle node becomes black and blue, black and blue. So the blue nodes are on the right, black ones are on the left. But this distinguished source node I'm not going to duplicate or split. And then, yeah, so then the edges are just carried like this from, okay, I think I got them the wrong way around in my picture. Okay, so now the black nodes are pointing to the blue nodes, and I have this like bipartition. There's one more pigeon because the distinguished nodes just became a pigeon. It didn't become a hole, and that's how we transform end of line into pigeonhole. Now, for a reduction, I should also tell how the solutions map back. So, at least in this little picture, what are the solutions? Well, it would be this pigeon that's left alone. It's not being mapped to any hole, but that can identify a sink in the original instance. So that would be the G mapping an empty pigeon or an unmapped pigeon into a sink in the end of line. Similarly, in this construction, if you're going to ever have a hole that doesn't receive a pigeon, that would be mapped to a source node in the end of line instance. Okay, so I hope that maybe this kind of got our reduction senses tingling. You can also do a reduction in the other way, but let me skip that. They're just different formulations of the same problem. So, okay, so why did I bring up end of line? Well, it's another problem that captures a whole class of problems. So there is this class called PPAD, which
Just a
stands...
question, like if you're answering one, then either like pigeon one, if it has no successor, then it's a pigeon, and otherwise you look back and that's a hole that is, wait, no. What, yeah, how do you deal with the yellow case?
Okay, let's see. So what if this was my graph? So the yellow guy wasn't mapped to anything. It produces a guy where the, I guess I should indicate that this will be the yellow node. So if the yellow node is not mapped to anywhere, it becomes a solution for the pigeonhole, but then it's going to tell us that actually the original yellow didn't have a successor. So that would be one of these boundary cases.
Right.
So it's also a solution for end of line.
Now when it has a predecessor?
So, okay, so if...
or is it just
you're
annoying?
saying if the end of line instance, the yellow has a predecessor.
Yeah, that was the one I wasn't quickly able to figure out. I guess it can be done somehow.
Yeah, let's say I just syntactically forbid the yellow node to have a predecessor. Just like define my graph in such a way that, yeah, let's say I hard code the predecessor pointer of the yellow node to point to itself, just to make sure that there's no way. That's one way of taking care of it. I'm sure there are others.
Okay, makes sense. Sure.
Yeah. Okay, so there is this class called PPAD, which is just all problems in TFNP that reduce to end of line. And so PPAD stands for Papa Dimitriou. He introduced this, inadvertently named it after himself. I guess really it's called polynomial parity argument directed version. So it's a mouthful, but you know, you just have to live with this. It's what these guys came up in the 80s, early 90s maybe, forget. Okay, so let me draw a picture of what has been known about these classes since, yeah, like the early days, and how our understanding has developed. So we have...
Can I ask a question?
Sure.
So those classes PPAD and PLS, they are defined as reductions to a search problem.
Yeah.
But in decision problems usually define complexity classes as restrictions of the power of the Turing machine. So is there any way of interpreting PLS and PPAD as restrictions also to to the power of the Turing machine in some way?
Yeah, so you're asking if there's like a Turing machine model that defines the class. And I think the short answer is kind of no, that these classes are often defined by just telling you what the complete problem is. There's an artificial way maybe of formulating these classes based on like some kind of a Turing machine that like implicitly somehow embodies the combinatorial principle defining the class. But I don't think that's very useful. So I would just say, yeah, just think of the classes as admitting a complete problem, and they're defined by the complete problem.
Okay, thank you.
Okay, so I'm going to define this or draw this diagram. So we have the set of all TFNP problems. So this is a very unruly class. They don't really have, as long as we know, they don't really have a good, like nothing to do with each other. This, for example, we don't believe that this class has a complete problem. So it's a kind of maybe a semantic class, as sometimes is said. But then, you know, we study these subclasses that have like simple natural complete problems. So we said there's PLS for the iteration problem, and then there is PPAD for the essentially bijective pigeonhole. And so they're both subclasses of TFNP. So, once you have two classes, you can also consider their intersection. Like you might, even if it's not natural. But so let's try. Take the intersection of PLS and PPAD. So any problem that's reducible both to iteration and end of line. So this is starting to be a class that's kind of, well, the search problems become easier and easier. But a priori, it seems like an artificial class, right? It's, maybe the analog is the class NP intersect co-NP. That's a kind of a weird class. It's kind of semantic, doesn't known to have complete problems. Like you can syntactically define such things, but you're not guaranteed to get anything natural. And so that's one reason why 10 years ago, really the founder of the theory, Papadimitriou, and his student Daskalakis defined a natural subclass of this intersection class called CLS for continuous local search. I'm not going to define it exactly, but it's a kind of a class where the complete problem tries to capture the complexity of kind of gradient descent methods. So somehow the complete problem is that there's a Turing machine that computes a continuous function from maybe let's say the unit square in the real plane to the reals, and you're trying to find some sort of a local minimum of this continuous function. That's all I want to say about this class. Even defining is really awkward because you have to. It's not as combinatorial as what we have seen today. You have to somehow encode real numbers with floating point precision, stuff like that. It is natural for people who do machine learning and try to find these local minima of continuous functions, but I've always thought of it as a bit like a class that's a bit not like the classical classes. So this was defined by Daskalakis, Papadimitriou in, 10 years ago. And going lower, there's a class that's very important for us today, and I like it. It's again a combinatorial class. It's called end of potential line. So this will be a problem that very much in a natural way marries the DAG-like properties of this iteration of having potentials and yet having a graph that's contains like a disjoint. It's a disjoint union of paths. So these two properties are going to naturally be married by this end of potential line class. Still yields problems that we don't believe are polytime solvable. So below all this is the class FP, which is simply these search problems that admit polynomial time solutions. And we basically believe that all of these classes above do not. It's just that, so you can't hope to, of course, separate any of these classes because that would imply B not equal NP, but we're still trying to prove a theory that is useful. I should maybe mention that this end of potential line class was only relatively recently defined. So there's works of Hubacek and Yogev and a bunch of other people. So for people who study TFNP classes, one of the big motivations for our class is that it contains many natural problems. And they've certainly shown that even classes this low contain interesting search problems like parity games and problems coming from, I guess, algorithmic game theory and stuff like that. Not a huge expert on that. So this is basically the status before this year. And there was a huge breakthrough this past year at Stock 2021, where I wonder if people have heard about this. So best paper award for the result that in fact CLS equals this intersection class. So this was shown by a bunch of people, Fernley, GHS. H here is Alexandros Hollender, the guy who's also part of our current results. So this was published there. So it's amazingly surprising, because the whole motivation for defining the CLS is that this intersection class didn't seem natural, and you wanted a natural problem. And like they very explicitly like made this jump, you know, thinking that there won't be a collapse of classes, but okay, these guys showed that there actually was. And the paper is pretty long, because you have to translate this PLS, PPAD problems which are combinatorial, and somehow make them into this kind of continuous world of real arithmetic. But yeah, so this was a breakthrough this year. And when we started our project, I wanted to separate classes. And actually, when I actually read a research statement by Hollender where he said, okay, we just proved that these two classes collapse. So of course, what we should do next is to show that such surprising collapses cannot happen again. Like, this was already surprising. Let's at least show that this end of potential line problem is different from CLS, equals PLS intersect PPAD. So for such separations really mean, again, prove them relative to an oracle, where these circuits that are given are thought of as black box. So then in that kind of a model, you can prove unconditionally separations of classes, and such a thing would be evidence that the real Turing machine classes are also distinct, because you can't prove them the same using the techniques we know. So techniques that just treat the circuits as black boxes. But lower bounds are hard, and so the way you would approach these questions, and this was already begun in the 90s, is that if you want oracle separations, it kind of boils down to questions in propositional proof complexity. So each of these classes embodies some combinatorial principle, like this iteration and a pigeonhole principle. And an oracle separation follows if you can show that those two combinatorial principles do not reduce to each other in propositional proof complexity. So the notion of a reduction there is a shallow decision tree reduction, or alternatively, it's like a tree-like resolution proof. So you have two unsatisfiable CNF formulas, and you show that one doesn't reduce to another, meaning there's no efficient tree-like resolution proof of one CNF formula from another. And that's what these questions boil down to. And so we really want... Yeah.
I should have asked this question like 5 minutes ago when I was hesitating, but now I realize we're getting further and further from it. So let me break in. Okay. Sorry, I was just thinking about this bottom of the picture, FP. Like the fact that it sits there at the bottom, do you like prove it via reduction, or is it more like vacuously, like then you can just solve the problem and afterwards build whatever like default instance you like, or how do I see that FP is at the bottom?
The reason is that you can, if you have a problem in FP, it reduces to any problem because you can just solve the problem within the reduction. Like, we allow polytime reductions, so you can just solve the, so okay. So trivial reasons.
Basically, I just build it. Yeah, okay, makes sense.
Yeah. So to fit the formal framework, I guess you would have to build some like a very like trivial,
But I see. Okay. Yes. You have polynomial time in the reduction, and that's it. That's yes. Thanks.
Okay. So I really wanted to start exercising my newfound proof complexity interest and separate the two classes. So we worked on this for, well, I don't know, close to a year or 10 months. And like lower bounds they're considered a lot harder. Like we just saw reductions. You just have to give an algorithm basically of massaging one problem to another. But how do you prove that you can't reduce one to another? So this turns out it's to be so hard to separate that it's actually impossible. So we actually found a further collapse when we finally had the guts to like change our mentality and consider the opposite eventuality. So we show, and I'll prove this today, that this problem, which I haven't yet defined, end of potential line, just further collapses to this intersection class. So it really shows in hindsight that this interclass is rather natural, because so many natural problems turn out to be equivalent to it. So I already said that, so it's a collapse. I'm going to give you a reduction today. And so it's easy, like you can understand all the details of it. It's also fully combinatorial. Somehow the CLS, by definition, was sandwiched between end of potential line and the intersection class. So this new theorem, it gives as a corollary this breakthrough result. So yeah, you'll see a simple proof of a like best paper worthy collapse today. So, okay, like now I feel like I've advertised this enough that we might take a break right here, and we'll come back with actual trying to prove this. But just let me just, so this is what I want to do today. Let me just mention maybe before the break, like what other results we can prove. So this is just for kind of overview. I wonder how, if it's just going to confuse you more or not. But here's all the results we currently have. So we can show a collapse here. So that's a long equality sign. But okay, so there are also other classes we'll see. So there's a classic class called PPADS. I'm sorry that these things get kind of convoluted. Also defined by Papadimitriou. It's if PPAD was bijective pigeonhole, PPADS, so S stands for sink. You're only allowed to find sinks, and that turns out to be equivalent to injective pigeonhole. There's also a class, a newer one. So end of potential line is new. There's a variation of it which is called sink of potential line. Hasn't been studied a lot. Turns out, okay, so there's an inclusion here. Another of our results is that we can also characterize not just end of potential line, but also sink of potential line. So this guy turns out to be, actually, it's an intersection class. And the diagram already tells you what it should be. It's the intersection of PLS with PPADS. So that's a kind of a byproduct of the collapse.
So why isn't PPADS contained in PLS? Because you can just iterate and find the sink? Wouldn't it work?
So the problem is that with the pigeonhole or end of line problems, there's no potential. Like the graph, this is just intuition, of course. The graph is just the paths can go from any node to any other node. So there's no guarantee of a potential that's kind of diminishing at every step. And in fact, there is a separation. So that's actually one of our newest results is when I now draw a dashed line, I mean the two classes are incomparable, again, in the black box model. So you can't reduce PLS to PPADs or the other way around. They're just incomparable. So that's another new result we have. That's actually the one that I mentioned in the abstract, talking about like its proof, like this result phrased in the language of proof complexity. An old result prove that PLS is incomparable to this PPAD. Can also show sink of potential line is incomparable to PPAD. So in short, the diagram I've shown you here is it's full knowledge. We know all the inclusions that are true, and we have black box separations in cases where we can't show an inclusion. So we get like full picture for at least these classes. And yeah, these feature classes from the original papers. There are a couple of classes which I haven't drawn here called PPA, some mod 2 analog of PPAD, and some PPP, which is some Pigeonhole class, one of the most powerful ones. But yeah, I'm not going to put them in this picture. Okay. Let me define end of potential line before the break. So then you can just start like mulling over it and trying to see if like what the content of this theorem is. Okay, so let me define that. End of potential line. Okay, so this is supposed to marry the two problems we have seen. So here the input is, so we're given a successor circuit, predecessor circuit, and this potential value circuit. Okay, so what kind of a graph do these guys define? Okay, introduce some nodes. So again, you should think of the potential values in my pictures as increasing when you go down. So now the successor and predecessor, they're going to give a graph which is a disjoint union of these directed paths. The potential values for every step are supposed to increase. So that means that every path is going down the grid. So that's kind of the instance that results. We have a distinguished source node, which is promised to have this one successor. And what should you find or output for such a graph? Well, a sink or a source. Well, source that is distinct from the distinguished source node. And then again, there is in parentheses, if the distinguished source node is not pointing forward, then that's also, you can also output that just to make this problem total. So in the picture, what are the solutions? Here's a sink, 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 but also there's a source, which non-distinguished source, non-distinguished source. So those are the guys. So I think it should be clear from the definition that this is, yeah, it's in both PLS. So it's reducible to this iteration principle because you can just forget that you have predecessor pointers. Just drop P and it's a valid instance of iteration. And it's also in PPAD. Well, here you can forget that you have potentials. So you can ignore V and just have successor and predecessor access. So somehow the claim is now that this problem, it very naturally marries the two iteration and end of line into like a single problem. And yet it just wasn't clear that this natural definition in fact captures the intersection class by all these previous works. Like we were confused for a long time too, and we were surprised that the picture is this clean. Okay, so yeah, let's take a break here.
So thanks a lot, Mika, for the seminar so far. And just before we officially break, are there any questions at this point? before we take something like a 10-minute break. Please do feel free to just unmute and ask or put anything in the chat.
Can I just ask about the big picture with the reductions? So I guess the non-reducibility of the things on the right to PLS is some older result, right? Depending on the hardness of the pigeonhole principle.
Yeah, so maybe I should have mentioned this. That the way you prove black box separations, the ideal strategy is you take a principle and you turn it into a proof system. Like, what is the proof system that proves like exactly that combinatorial principle and not more? Turns out PLS is, in this language, characterized by resolution, or really bounded with resolution. And these are new results too, by the way. So this is old and classic. What we can now show is that PPAD is characterized by null Stellensatz over integers with small coefficients. So whatever that means. And also we have new separation involving PPADS. This is characterized by Sherali-Adams proof system with small coefficients. So you want to separate in a black box, you separate the two proof systems. So for resolution, you care about width. For these null Stellensatz, blah, 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 it's degree, the defining measure.
Any other questions? Otherwise, thank you so much, Mika, for this first half. So we're back after the break, and Mika will continue with the technical details about this result. Please, Mika.
Okay. Hey, we had good retention, same number of people. I managed to advertise the result well then. So let me just maybe recap the three problems that we're interested in, just to kind of highlight the differences and challenges for this proof. And I guess the intuition why we didn't even believe that this was true. So we had the iteration problem where the input defined this DAG. And what's important here is we only have successor pointers. So if I'm some kind of a node here in the center of the grid, I can only kind of jump to my successor. But if I'm like a polytime Turing machine, there seems to be no way of knowing who's pointing to me. There's just no predecessor access. In particular, I could have a node and everybody above me could be pointing to me. So like there is like highly non-path-like, because everybody is just kind of converging. Several different paths could merge at one point and continue. So that's a challenge. And then we saw the end of line, which is basically the pigeonhole principle. So we had like one perspective was we have just a disjoint union of directed paths, no potentials. So there's no sense in which when you walk along the path, you're making any sort of progress. Like you could imagine being stuck in actually a cycle in the graph. Like no matter how long you walk, you're just not going to find a sink. But somehow if you take these two problems and combine them, consider the intersection class, then what remains, like that intersection class we claim can be very nicely characterized by this problem that clearly incorporates both kinds of aspects of iteration and end of line at the same time. But again, like the challenge is somehow in this end of potential line problem, we just need to end up with paths, whereas at least the PLS problem, many things going on. So let's start developing this proof, putting a few reductions together. And I think so. I need to define a fourth problem, but I promise it's the last problem I define. It's just a very useful, maybe at least for us, it was a new type of combinatorial principle, if you want. So for now, we just call it path pigeonhole principle. And I guess the number of pigeons you could vary, but let's look at just the case where you have 2 n pigeons, n holes. So what does this look like? There's a sense of a path mapping. So I have some 2 n pigeons like this, and they're supposed to be mapped to only n holes. So maybe n holes here. So it's very much like a weak pigeonhole principle, but the mapping is not, it's given by long paths. So really the instance has a whole structure where you have intermediate nodes. And what this input looks like is that each of the 2 n guys at the bottom are supposedly starts of paths. So these paths, they go down, and they're supposed to end up amongst the n holes, except you can't fit this many holes into this many pigeons in this many holes. So you're going to have violations to this path property, or violations to ending up amongst the allowable holes. And those violations count as solutions to the search problem. So maybe we just draw a bit of an instance here. Okay, so this is like some kind of a pointer assignment. The input so gives me bidirectional access to these. So you have, for this problem, all the 3 properties: successor, predecessor, potential. The potential's increasing when you go downwards. And what are the solutions? Well, it's going to be a violation of this path property if you don't end up amongst the n holes. Like this guy is just ending in the middle of nowhere. That's a solution. This guy is not amongst the n holes. That's a solution. There's a solution. Oh, I should maybe make this picture a bit more general. Let me think. If I add this pointer, it goes into the allowable region, but it created a source. And there are also some pigeons here that aren't even parts of paths. So it's like weak pigeonhole, except the mapping is given by long paths. So I guess I can allow some n steps for these paths.
And just to double check, you will never have 2 pigeons going into the same hole, because you have these back edges that uniquely identify the predecessor, correct?
Yeah, so when I'm drawing these, I kind of draw the graph determined by the successor and predecessor relations. I only draw an edge if there's a bidirectional pairing. So that's why in my pictures you don't see 2 pigeons kind of mapping to the same hole. The hole would pick one amongst the 2 pigeons, and that's the edge that ends up in my picture.
And the other one would then be a sink, right? I guess. Like if it has a forward edge that is not mapped by the successor, then that means that there was no edge. Is that the way to think about it? Yes. Okay.
Yeah.
Great. Thanks.
So it's like, given any functions for successor and predecessor, I define a graph which is always going to be a disjoint union of directed paths. And in this graph, I'm looking for these sinks and sources as solutions. Okay, so the punchline about this is that we can. Okay, so this is. I remember thinking about this, but we somehow came up with this path pigeonhole sort of principle, and we were trying to show that it's kind of incomparable to the usual pigeonhole principle. This is where we were trying to prove lower bounds. But it's actually not hard to see that this principle is not incomparable to the usual pigeonhole principle. So pigeonhole principle with n pigeon, oops, let's use some colors, n pigeons to n minus 1 holes. So this is the version where there's a direct mapping, like one step. I claim you can reduce this to this path version, even though the path version is sort of a weak pigeonhole. So we know from proof complete you can't reduce the usual pigeonhole to weak pigeonhole. The weak pigeonhole is really, I guess, do you say a stronger or weaker? Pick your like favorite way of thinking about it. But it's, yeah, classically it's certainly true that this, you can't reduce pigeonhole to weak pigeonhole. But if I allow the paths, the mapping to be given by paths, then you can. Okay, so this is very easy actually to show. So I'll just, yeah, draw pictures for these reductions. So you start with this pigeonhole principle. So I'm going to maybe draw it like this. So here's my n pigeons, and they're going to get mapped in one step amongst n minus 1 holes. So that's the search problem I start with. How am I going to create an instance of this path pigeonhole? Well, it's going to have n layers. And I'm going to take my pigeonhole and insert it or copy it or stack multiple such things on top of each other. So I'm going to take this green thing, put one copy of it here. So I guess here I would have 2n pigeons. Here I had my n holes. And once I plug a single copy of this n to n minus 1 in the first layer, on the right, on the left, I'm just going to hard code pointers that just go downwards. So that's just hard coded in the reduction, but the remaining half the pigeons is kind of coming from the problem I'm reducing from. So that's like, I've now taken 2n pigeons, and after one step, I have 2n minus 1 left, in some sense. So what does this look like more generally? In the next step, I'm going to copy another, yeah, that's another copy of the pigeonhole on the next level. And I'm going to repeat this. I'm going to get this sort of an instance. And then at the end, okay, so in some n steps, I've managed to somehow reduce the number of pigeons from 2n to just n. And everything that's outside of these copies of pigeonhole is just these hard-coded downwards pointers. So they're not going to be associated with any solutions. The only kind of solutions to path pigeonhole happen inside the green regions. And so if there's a solution to path pigeonhole, so it means that maybe there's a small picture, but maybe there's a node which is not mapped to anywhere. So that's so these things exist in the pigeonhole principle. So that's a kind of would be a violation of the path pigeonhole. But you know, this solution came from the original instance, right? So every violation, or rather a solution to path pigeonhole, I can trace back to a solution of the pigeonhole principle I started with, that instance. So I've done nothing but just copy this one pigeonhole many times. Actually, I have maybe a better picture that I drew. So here, maybe kind of more in detail. So the green guy is the instance to pigeonhole. So you can't, yeah. So it's going to have unmapped pigeons, but every unmapped pigeon here, for example, here's another who doesn't have a successor. Well, it's the same instance, so this solution is going to get repeated at every layer. But all those things, it came from the original Pigeonhole instance. I wonder if this is, yeah, I feel like I'm just repeating the same thing. So yeah, I guess any questions? Is this sort of believable? Jakob, ask something.
No, it makes a lot of sense, but I'm just thinking that actually what you're saying is, I mean, there's nothing magic about the 2n here. You would allow me to insert any polynomial in n? So it's like, in some sense, you reduce even to the very weak Pigeonhole
Yeah,
principle.
that was my next point. So, I mean, the same principle that the choice of parameters wasn't so crucial here. I could have gone even lower, and if I had, let's say, n squared levels, I could go all the way down to have, so n squared pigeons to n holes. I would just have to have more levels in my construction.
And I was thinking about the other direction is obvious. Like that I can take a path instance and reduce it to the classical just by composing, I guess, or I need to play with the parameters a little bit.
So I think this path pigeonhole is strictly stronger.
Ah, okay.
Yeah. But
Mika, do you think, just my question regarding your opinion on this, I think it's hard to prove it. Do you think that, referring to Jakob's question, do you think that any polynomial would work instead of n square?
oh yeah, sure. So yeah, so one has to remember that this capital N comes from it's exponential in the input length. So I guess when I'm squaring something, when I'm squaring capital N, it means I'm creating a circuit with, I guess, 2n input bits. But nothing prevents me from even going from n input bits to polynomially larger. So, you know, you could even have like quasi-polynomial gaps. It's just important that you end up with at least n pigeons at the end, because you know, you can't, I guess, compress more than to n pigeons. That was the initial width of the pigeonhole instance I gave you.
Can I say something about the other direction? So, from how I understood the path pigeonhole principle, if you could satisfy it, then it gives you just a bijection between any two adjacent rows. So, particularly the edge of the last row are a bijection from +1 to n.
I guess that's sort of the problem. It's not that every two rows gives a bijection. So let me try to
But how that
modify
every
my...
row had an edge down to the next row, I thought.
So if you look at, let's see, this level, so there's a perfect, like, there are no solutions there. Like every guy who's part of a path is going to be part of a path. You know, the paths continue. There are isolated nodes that's not allowed in a perfect bijection, right?
Mm-hmm.
So, yeah, it's not quite true that.
Okay.
Yeah, but by the way, these things are something I haven't super deeply thought about. But my sense was that this was actually strictly a stronger principle. Anyway, so this is our main building block. And what it kind of allows us to do is intuitively, it allows us to, well, compression. So if I have many paths, well, quadratically many, n squared, it allows us to kind of, in the presence of the pigeonhole principle, it allows us to, well, compress. So that's something we're going to use.
Mika, sorry to interrupt. Just one question. Do you have the restriction that at every layer you're reducing by 1, or could you just in the path PHP, or could it be just that the second layer is actually the same size as the first layer?
Can you say again?
Like the number of vertices per layer, does it reduce from one layer to another, or?
Good point. I would, yeah, it doesn't really matter for us. Let's say not. So, yeah. So maybe every layer has the same number of nodes, but then you only should arrive at half the ones at the bottom.
But what would be violations along? Okay, maybe it doesn't matter what the violations are along the way. There's another question that is somewhat related, maybe in the chat. Massimo was asking whether there are constructions which are more efficient in terms of layers.
Well, my sense is that this is optimal. Like if all you can do in a single, like if you're given a pigeonhole guy, you can't go from n pigeons to half n pigeons in one round. That's certainly true, because the weak pigeonhole is truly, I guess, weaker than the normal pigeonhole. Maybe you can go like, instead of losing one pigeon, you lose polynomially many, or I guess handful. I don't know.
Like presumably, I'm thinking like logarithmically many might be. It depends. I mean, you have to redefine the path PHP, right? But if you're allowed to skip like say a constant number of decrease by constant number of pigeons per layer, then I guess you could somehow compose on the standard PHP side, sort of do this thing, except that I put part of it in the reduction instead of in the final graph, if I make sense.
Yeah.
But it's sort of doubtful whether that reduces the layers in some meaningful sense. I'm not sure.
Yeah, so here's a result.
Also, I'm not sure if I'm interpreting Massimo's question correctly. So Massimo, please feel free to like clarify or protest if I messed up.
So that's certainly true. And this is a non-trivial result that, yeah, it's also have to do with, if I look at end of line, I'm guaranteed to one start of a path. But what if I'm guaranteed 2 starts of a path? Seemingly a different problem, but turns out you can reduce between these 2 versions. And this holds for certainly constantly many, but even like log capital N many, I think. So this is, Alexandros has a paper about this in the TFNP context. In proof complexity context, I don't know if it's been.
I mean, in the TFNP context, I guess if I want T starting vertices, I just make like T copies of my problem? Or do I need to do something more
so you're saying,
than that?
You're saying that this is easy. Yeah, so it's easy to kind of multiply starting path, because you can just take copies of your instance. But going the other way around is non-trivial. Yeah, reducing.
Yeah. I'm not claiming anything as much as asking. So just to be clear.
Sure. But so one thing interesting here is that something that's been done in the language of TFNP could have been done in some faraway proof complexity land too, because you're studying the same kinds of problems in different language, and sometimes it happens the same thing is proved in different communities. So it could be. He's really interested in these connections, actually. Okay, so let's move forward. So I now want to sketch this main reduction. And well, I'm going to start with what is a complete problem for the intersection class, which is, as promised, a bit unnatural, as you would expect. So the canonical complete problem, it's something like this. You take the iteration problem and then and the let's say end of line or pigeonhole principle problem, and I claim that there's some anding of search problems that I'm going to define in a moment, but this anding will give me a complete problem for the intersection class. It actually works for any classes. I'm just doing it now specialized to PLS and PPAD. So what is this AND problem? The input to the AND problem is a instance X to the iteration problem, but also you get an instance Y to the other problem. So yeah, just two instances, and the challenge is to solve either one. So you get to decide. So you can output a solution to the iteration problem or a solution to the PHP problem. So at least in the TFNP world, these intersection classes, if the classes you started with had complete problems, which often is the case, that's how we define our classes, you can define complete problems for the intersection classes by this operation. But of course, like, it's not the most natural problem in the world. It's in fact very artificial. But yeah, our challenge is to take this. So I hope it's kind of intuitively clear. Just maybe for completeness, let me say, like, why is this AND problem in PLS? Well, you just forget the input Y. You just work with X. You solve X, which you can do in PLS, and you output a solution to X, and that's valid. So yeah, people believe that this is a way to construct complete problems. Okay, so this will be the starting point of our reductions. I want to start with PLS, the intersection class, and reduce it to the end of potential line. So let's take a first stab at it. So I start with the AND problem. And I want to reduce it. Well, let's not go all the way to end of potential line, but let's go to sink of potential line, which I didn't define yet. I'm going to do it now. So very simple variation of end of potential line. So what is sink of potential line? It is same input, but as output, you just have to find a sink. So in this case, these are not allowed. Okay, so what are the sources in my picture? This is a source. You can't output that as a solution. Yeah, it's a source, but it doesn't count. Similarly here. So what remains are just these sinks of the paths. So it's a harder problem, right? So end of potential line reduces to sink of potential line, but not necessarily the other way around. So my lemma here is, let's at least go first to this sink of potential line. We're going to have one more step in the proof, but this is a starting point. And it's also like most of the key ideas are here. How are we going to use this path pigeonhole? So I could give a reduction like this, but it suffices if instead of this guy, I put here the path version. I just showed that PHP reduces to the path version. So let's use that from n squared to n. So that's really the reduction I'm shooting for. So let's just draw a picture of what this OR problem looks like. So first I have an instance of the iteration problem. Here I really want to draw good pictures. Okay. Okay, what does an iteration problem look like? There is the distinguished source node over here, and it's pointing downwards. Remember, I only have successor pointers here, and what's important is that the pointers could merge and continue forward. Okay, so as an iteration problem, really, I just have solutions here and here. So that's one instance. And then I'm also given this path PHP instance. So another part of the input describes this mapping of n squared into n. So so there's some path going on here. And yeah, I kind of think of this guy as a red triangle. So good. I mean, both of these instances have a natural potential to them. They increase downwards. So this is my input. How am I going to produce a sink of potential line instance? Well, here's how we're going to. I'm going to start with this, kind of build it on top of the iteration instance. So let's see. Okay, I think I can fit it in here. So, well, I should say that this n is, imagining this being also of width n. Okay, so first thing I'll do is each of these pointers, I'm going to expand a single edge into n squared edges. So I'm starting with my iteration instance, and then each of these edges now, I'm going to kind of make copies of them, that there are n squared copies. So that means that the nodes that I have in my instance, they're going to get replicated n squared times. I don't want to necessarily draw it here. But yeah, they're just copies of each other, and they become these parallel paths. Okay. So now, since I have n squared parallel paths going on all over, I'm going to use the path PHP to compress these n squared pigeons into just n pigeons. So for every edge in my iteration instance, I'm going to insert in the middle of it this compression gadget. Okay. So that's just going to get inserted everywhere. So that, after you kind of apply that, you only have n pigeons or paths remaining after the gadget. And now something interesting has happened. Something interesting right around, let's say, this green node. So earlier in the iteration instance, multiple guys at the previous layer could have pointed to it. In fact, n guys could point to this one node. And this node doesn't have predecessor pointers, so he would have no clue which nodes are pointing to him. But this is now fixed. We've locally made it path-like, because in my new instance, what's the number of paths that can arrive at a node? Well, I have n guys at the top. Each can route n paths to me. So you're going to get, at most, n squared paths at these new nodes. Let me kind of zoom out a little bit, like what is happening here. Just kind of expand the construction a little bit. So here's like an expanded view, bloop. So I had these, I replicated that one node. It's like n squared times. And that's now going to be partitioned into n buckets of size n each. And And those n buckets are going to hold the these n paths coming from different directions. So in my instance, I guess I would have like one node above is sending n paths. Then there's another guy sending its n paths here. The middle guy, so this guy here, doesn't exist. So those paths are not coming in. Yeah, and then I'm going to continue n squared paths forward. So in this fashion, I've created predecessor pointers, because if you name any one node here, now let's take a look at this one. I know which bucket it belongs to, so I know which guy at the level above I should be querying to see if it's sending me, it's pointing to me. So now I've, with this bucketing, I've created a way for a guy in the middle to know whether it's being pointed to. And there's only one candidate guy above could be pointing to that very node. So for example, here's another node contained in a bucket where the guy above it is not pointing to it. So it's just going to create, in this instance, a starting point of a path. So this is the description of the construction of the reduction. I still need to prove it correct, but any questions about just the construction of how these two instances were combined into one?
Can you say again what reduction you're doing here?
So I'm taking iteration, which is on the left, I have an iteration instance. On the right, well, I said I would want to do it from Pigeonhole principle, but I already reduced Pigeonhole to the path PHP. So that's what I have here. So this is path PHP. And this was iteration. And I'm producing a sink of potential line instance. So again, sink of potential line means you have these downward going paths, the disjoint, and you need to find a sink.
So you showed already that the pigeonhole principle is reducible to the path one. So
yeah, so I
intervening step with iter or the path one going to that other thing. Okay.
Yeah. So yeah. Okay, I could have written it more clearly.
Can I rephrase, Mika, just to see if like one way of thinking of it, like I didn't get where you put your red boxes, but I think, so I guess, let me focus on the second layer.
Yeah.
And mentally, like at the second layer, I make n squared copies of this every node.
Yep.
And I guess the way I'm going to use that is that I'm going to do bucketing. So now I have like n buckets of n each. And then I know if there is an incoming edge from some other vertex which has an index, then I guess it's gonna end up in the, wait, am I going to do some in the ith bucket or something I wanted to say? And then the problem is now that I don't want n squared outgoing edges because things are going to balloon. And so now I do compression, I guess then I do compression. Or yeah. What is I'm struggling a little bit to see how this fits together, but was that like an equivalent way of saying it, or I'm missing something?
Yeah, I think so. I still have to prove correctness though. Like I want to say that every solution of this resulting instance is a sink of potential line instance. It has some solutions. Yeah. I must be able to trace back those solutions to a solution to one of the two instances that I started with.
Yes.
Okay. Okay, so like what are the solutions of the resulting instance? So they are sinks. Well, where do I have sinks? I have sinks, especially here at the bottom. So n sinks even here, n sinks here. But those I can trace back to the solutions of the iteration. Like the paths ended there because the iteration problem had those paths. Those sinks. Another source of solutions is inside one of those path pigeonhole triangles. So they certainly, like when I compress, I'm certainly losing paths. But if you ever find a place, like a solution in a triangle, well, that triangle is just a copy of one of the instances. So then you can trace back these solutions to the triangle. And those are the only solutions. So what's important for this reduction is that the one part I highlighted is that the green blow up. So there I did not introduce any solutions, because what's happening inside the green blob is maybe I create paths. So some paths are starting, I'm creating sources, but for sink of potential line, sources are not counted as solutions. So yeah, so this reduction is, I think, the whole key to this proof. It's an interesting way of, taking two instances, combining them into kind of only like one, having only one type of solutions, which are sinks in this resulting sink of potential line. And the sinks can come from either one of the two instances I started with. So yeah, this is the crux. So I want to kind of pause and ask if I should clarify something about this.
Mika? I just want to rephrase out loud, so maybe I understood. So basically, if you have a DAG with multiple in degree, with a large in degree, I just multiply each vertex so that the incoming edge, there is one incoming edge for each copy. So at some point, this would, for every layer, this would explode. So I could think that I'm maybe layer by layer, I'm compressing the n cube to n square, like incoming, like copies of the vertices, I guess. I mean, I don't know. I'm thinking that I'm putting the triangle in the green block, but I'm putting like n of them. But I guess it's exactly the same because, of course, just it's just a visual. It's just a visual interpretation. But
yeah. So it's like if you look at my green blob here, I guess one different way is saying, okay, I have n guys going out, but let me just compress them right there. I maybe just chose one way of inserting these triangles kind of along the edges.
Okay, thank you.
Okay, so I have one more step of the proof remaining because we only got to sink of potential line, but I want to go all the way to end of potential line. So like what I want to do, I would, can I just complete the proof by continuing the reduction onto end of potential line? Answer is no. So sink of potential line does not reduce to end of potential line. That's actually so it somehow follows from here, like end of potential line, it's included in this pigeonhole in particular. But now we can show, like one of our new results is to show the sink of potential line is incomparable to pigeonhole. So okay, like where did we get if I can't continue my source of reductions? Well, let me make an adjustment. So what did we just see? So we have that started with PLS intersect PPAD, and okay, I can write it kind of in a silly way as PLS intersect PPAD intersect PPAD. And okay, so we just showed that this intersection class reduces to some sink of potential line. By the way, I'm maybe confusingly using sink of potential line both as a problem and the class of all problems that reduce to it. This is sometimes done. You know, maybe you don't want to invent another name for the class as you have for the complete problem. But just like, let me keep this intersection PPAD with us. So the final step is to take this intersection class and reduce that to end of potential line. So what remains is to show that sink of potential line, or, so I'm taking a complete problem for this intersection class, or pigeonhole principle, reduces to end of potential line. So that's the final step, and the proof is easy. Okay, so let's see this. It's another reduction from an OR problem. So again, I want to draw good pictures. So let me draw here on the left a sink of potential line instance. So distinguished source node, and it's pointing always downwards. Let's see. Okay, so that's my sink of potential line instance. What are the solutions again? Only sinks. So this guy's a solution, these ones, but the sources are not solutions. Like end of potential line, I need also the sources to be, but how do I do that? I need the help of the pigeonhole principle. So that's the second part of my input. Let's say n pigeons going to n-1 holes. So I'm going to use this graphic for it. So those are the two inputs I'm given, and I need to produce an end of potential line instance. Let me try to fit everything in here. Okay, so here's my reduction. So I start with, I just copy the, okay, just copy this guy over here. Let me just make a bit more room. Okay, so far I've just copied the sink of potential line down, and I've reserved room above, like another bunch of nodes of like lower potential. So the instance above, I'm just going to fill with the sink of potential line, but mirrored. So I want to mirror things because I want to turn sources into sinks and vice versa. So let me just draw that. So on the top, I just mirror. So the blue edges, they get mirrored like this. Fiddly. Okay. And okay, a perfect mirror would have these guys pointing upwards, but I reverse the direction of edges. So I make them point downwards. Okay, so they're going in the right direction of potential. So in this instance, we should remember that both sinks and sources should be count as solutions. And so in particular, like all these guys are now sinks, but I don't want that, because if you remember, those sinks came from sources of the original instance, which are not solutions. So instead, whenever in the above part I reach a sink, I just add an edge to its mirror twin in the original instance. So all the sinks above, they just point to their mirror twin below. Okay. So I haven't used the pigeonhole principle yet at all. I just manipulated a sink of potential line into this. So what are the ends of lines? So sinks and sources here. Well, let me highlight. This, and sources, this, and this. But everything I've highlighted, it originally came from the solutions to sink of potential line. So all the solutions I currently have, came from the right places. I can trace them back to solutions to sink of potential line. But what's the problem? Why am I haven't used the Pigeonhole, so I mean I have to use it somehow. But like, what's wrong with my current construction? Like every sink or source, every end of line can be traced back to a sink of line instance. So that's good.
We have a distinguished something here?
Yeah. So we don't have a distinguished node here, which is a problem. So that's what the Pigeonhole allows me to do. So I do a kind of a similar trick as before. So I have this instance. Now I duplicate every edge n times. So, okay, so I just put n everywhere. And I'm going to insert a copy of the Pigeonhole right here. So my earlier distinguished source node, so it's here. So I know that distinguished source node already exists. So I know that its associated yellow edge exists. So I'm going to put the Pigeonhole principle here. So that's a guy that takes in n pigeons, outputs, or n parts, outputs n-1 parts. So yeah, that gives me room. So here's my new distinguished source node. Okay, so maybe it has weight 1. So it's this, Pigeonhole allows me to make room for this new distinguished source. And so when I did this, I introduced some new solutions which came from the Pigeonhole principle itself. But those solutions I could already trace back to the Pigeonhole principle instance. And so yeah, that completes a proof, also completes my allotted time slot. So yeah, I guess I can take remaining questions about this proof, and maybe I'll just conclude with some open problems if you buy this reduction.
I mean, you were very close to proving that SOPL was the same thing as EoPL.
Yeah.
And you're saying that sort of morally SOPL is EoPL except for this annoying yellow thing, and that's where you like do this nifty trick of inserting a Pigeonhole, and then suddenly magically you're like back in business.
Mm-hmm. Yeah, these things can be very subtle. So yeah, without using this part, there's just no reduction. Like that's what we can show. So as advertisement, like where does that separation come from, by the way? Like we have a new separation showing that you can't, so going all the way back here. So this is the separation I'm alluding to. So this one. So we have a new proof that null stellar, because yeah, so that end of, yeah, we can show end of line. So you can't reduce sink of potential line to end of line. So in other words, you cannot refute the sink of potential line principle with low degree null Stellensatz. We have a new proof that so-called pebbling formulas cannot be efficiently refuted in low degree null Stellensatz. Fundamentally different proof that is more robust than previous ones. So that's, I guess, one point. So let me just say a few open problems. Like I like this TFNP study. It's new for me, but it's interesting that there's this whole theory of classes, which is kind of isomorphic to what we study in proof complexity. And I'm really hoping to like push this connection further and try to find more connections between these two areas. I guess Robert talked a few weeks about how there's like a third world that's isomorphic, which is this some circuit models and characterizing them using Kotchmer-Victorson games. Maybe a fourth world that might be isomorphic is bounded arithmetic. I know nothing about it, but I would be curious to see if like any of these kinds of techniques could be also be expressed in that language, and it would give something interesting there. I don't know, but I would have to talk to somebody who does bounded arithmetic. Okay, so I think, yeah, that's all for me. So thanks for listening.
Thank you so much, Mika. Questions, comments from the audience?
Mika? Can you hear me? Okay.
Yeah.
I have a question that is more like, it's not very technical, but it's more like about intuition. How do you interpret that problems like a gradient descent can be captured by the end of potential line? Is there like an intuitive level in which you could think of a gradient descent model and write it and express it into this end of potential line?
Yeah, I guess like there's an equivalence, but are you asking for like one direction of the reduction?
Yeah, one, even not a direction of a reduction, but one intuitive argument why you could write some problem like that in.
Okay. Yeah. So by the way, I know very little about these sorts of like real optimization, but I guess the intuition is that if I'm at some point in a Euclidean space and I have a continuous function I can evaluate there, I can evaluate its gradient, which gives me a direction where I can move so that my objective function increases, so my potential increases. And well, I mean, that's the basic kind of gradient descent type of algorithm. And yeah, so, you know, you get both like a successor function that is guaranteed to increase potential.
Thank you.
No.
Can I say something about bounded arithmetic?
Yeah, please.
So, I mean, you TFNP problems there as looking at the theories that prove the problems are total, but bounded arithmetic tends to study induction, and that kind of lives on PLS and things higher than that. And you'd need to work with slightly different theories to say things about these PPADs and so on, although you could do it. But just to say one thing from that, somebody was asking about machine model characterizations of these classes. So I think you can take PLS and say that if you have an axiom that every P to the NP machine has a computation, then PLS is kind of, that's for NP problems, you can prove a complete from that assumption. So I mean, maybe I'll ask for the details, but the point is if FP is like what you get from being able to solve problems in polynomial time, there's a sense in which PLS is like that, but starting with P to the n machines for polynomial time. And you can find a hierarchy of such problems above those with stronger machines.
So my understanding is that you can also prove some relativized separations in bounded arithmetic by starting with separations in propositional proof complexity. Is that right?
Yes, it's the bounded is just form propositional proof. So the bounded arithmetic separations, you've got to come down to propositional separations. But the arithmetic gives maybe a stronger way to talk about propositional proofs.
Yeah.
Maybe I can also ask you, you were about to mention some open problems at some point.
Oh, yeah, so the general philosophy is just to kind of push the this isomorphism of different theories further. So, you know, that's it. Like, what does it then mean? Like, what sorts of questions are open? So we have classes that are now kind of natural. Like this huge collapse here suggests that this class is, you know, worth studying. And so we don't, for example, have a proof system characterization of it like we have for these other kinds of classes. Look, how would you formulate naturally a propositional proof system that has the same power as, well, what this result says is that has the power of somehow both, like, well, it's like the join of resolution and Nullstellensatz. So we tried for a bit, but we haven't like found a really neat proof system characterization. So that's what you could ask for all of these TFNP classes. Sink of potential line is another where we don't, it's quite natural, but we don't have a proof system characterization. Then there are this, like the biggest separation I would like to prove, and that's still something like I think we're going to work on a little bit, is there is a really classic class still above here called just Pigeonhole principle, where it's the, I guess, strongest such class where you don't have, just have like successor circuits, and the solution is two pigeons who have the same successor, no predecessor circuits. So that's still, it hasn't been separated completely from, let's say, these other classes. So we'd like to show that, for example, that Pigeonhole class cannot do PLS, but that separation is unknown. It would follow if you could strengthen our current separation, which is like resolution width versus Sherley-Adams degree for low coefficients. If you could extend that to sum of squares. So somehow sum of squares can refute Pigeonhole in low coefficients, but if you could show that sum of squares does not simulate resolution with low coefficients, then you would have this separation. But that's still open.
So, but PPP is still, that's still what in proof complexity land would be called the functional pigeonhole principle? Like every pigeon gets exactly one hole.
Yeah.
So is there anything like if we relax and do the vanilla version where you just say, I don't care, there might be fat pigeons, but every pigeon goes at least somewhere, maybe to all of the places, I don't know, but any hole holds at most one pigeon.
So it's hard to say that a single pigeon goes into many places because you would have to have a successor circuit that specifies many different holes. But if you have successor and predecessor circuits, then you have an option. Do you count empty holes as solutions? So if you do, or if you don't, you get either PPAD or PPADS. So that was the difference. But if you throw predecessor circuits away, you just have successors, or how pigeons maps to holes, then you get this class PPP.
Mm-hmm. Right. So you then, I mean, and I guess you'd need some way of just asking about the, like you just asking about the pigeon and a hole, whether the pigeon goes there, but then maybe that somehow changes the game. Like rather than inserting a vertex and asking about the successor, just, you know, are these guys neighbors? Right.
But then the problem is, how do you certify solutions? Like for TFNP theory, you always need, like the propositional analog are bounded with CNF formulas. So you have to have a bounded with encoding. I should say, Papa Dimitri with students have a new paper on TFNP for kind of a polynomial hierarchy. So you could study unbounded with principles, where to certify that a hole is empty, you just have to kind of check that no pigeon maps to it. And even though you can't check that in P, you can check it in, I guess, like NP or something like co-NP, yeah. So in polynomial hierarchy. But yeah, that's a different direction.
Yeah, no, but I was thinking like empty holes are fine. I just want to find two pigeons that map to the same hole. But you know, one of these pigeons might be mapping to many other holes, but it's like sufficient that I find two pigeons that among the holes that they're occupying, there's one hole in the intersection.
How do you enforce that every pigeon gets mapped to at least somewhere?
That's an excellent question. Yeah. No, I was just trying to see that like the standard, the weakest form of pigeonhole principle over on the proof complexity side, would it like correspond to anything natural? But I guess the functionality requirement or the injectivity requirement is kind of natural, and it is very useful when you go over to this setting, I guess, is the conclusion.
Maybe I can just comment, like in a proof complexity perspective, like it's really natural to like encode all of these things in unary. Whereas when you're looking in the TFNP, it's really, really better to just think of everything as being encoded in binary. So like this functionality, we think about the natural encoding is to think about the pigeonhole principle as like a bunch of binary pointers that point to their holes. And the same thing goes all the way down with the PPADS and PPAD. So somehow these are like, this is like a natural way to get like logarithmic width encodings of these things. And this is somehow the space in which TFNP lives. Like the standard unary ways of encoding things are kind of less natural from this perspective.
I see. Makes sense. There is a question in the chat. So how come the coefficient sizes come into play in these correspondences? Is there a good answer to that?
It's a very good question. Like it is one of the things that came to us as a surprise. So here's the thing. Like, so we don't look at coefficient sizes so often in propositional proof complexity, but somehow looking at these connections brought about the importance of coefficients. Like just looking at wanting to separate these classes, which is natural for TFNP, raised this question, which you might not have looked at separately in proof complexity. So there's a sense in which there's a sense in which PLS is, so we're like doing a bit of a fantasy run. PLS is simulated by PPADS. So what is the complete form from PPADS? It's sync of line. So not end of line where both sinks and sources count as solutions, but sync of line. So only sinks count as solutions. And there is a simulation if you kind of allow unbounded coefficients. So what does that look like? Like here's my iteration instance. How do I turn it into disjoint paths where the sinks are the solutions? Well, you do sort of what we did. You kind of assign weights to the edges, meaning you multiply the edges. So in the first level, each edge that's present is just once. On the next level, I multiply each edge with n, because each edge could receive n guys from above, so I have to make room to route n paths downwards. And obviously, you get into trouble with multiple layers, because next time you have to use n squared, many levels and so forth. Like if you have many levels, these things blow up exponentially. So it's a valid simulation if you allow this multiplication of edges without bound. But we show that if you insist on bounded coefficients, weights, then you can't do it. So
okay, thanks. I guess technically speaking, for any of these proof systems, I mean, for all we know, like Shirley-Adams or SOS or cutting planes, or like the size of the coefficients could potentially not matter, but like they probably do.
So one corollary is that of this is the Shirley-Adams with bounded coefficient is different from Shirley-Adams with unbounded coefficients. Because actually what I just showed is not like a simulation of this iteration in PPADS, but with unbounded. Whoop. So we actually do separate, low coefficient from large coefficient.
Ah, that's nice.
Yeah.
Okay, any other final questions before we thank Mika again and wrap up? Yes, I guess that means we're about to call it a day. I'm thinking about, how to thank you, Mika. I guess I could try to say that, you wanted to provide us some light Monday afternoon entertainment. And may I say that we were, completely satisfied or something like that? So anyway, thank you so much for a wonderful talk. Thank you.
Okay, cheers, guys.